connection. Alessandro will start recording his own. And maybe I need a face of somebody. Salvatore, do you mind if I look at your face when explaining, so I know a kind of reaction from somebody?
The problem is that at that time on Monday, I cannot. I'm not a computer with the camera. I'm sorry. Okay. Tomorrow I will have.
Okay, camera. So tomorrow it will be your moment. So please, somebody can switch on the camera. So I have somebody. No. Okay, Alessandro.
Good morning.
Hi. Okay.
Thank you.
Okay, very well. No, I need to see the face of somebody, so I have a kind of reaction to what I'm telling, and this is useful for establishing the speed of what I'm telling. Okay, so I want to repeat something which I already said last time, because these are very delicate subjects. So I think it is very well to do the job in again, to repeat what we said. So last time we discussed this term in our integration by parts. We have a body, we have the boundary of a body here, which we call boundary of C star. And then on the boundary of this body, we have this integral, where PCB means the projection on the tangent plane of each face of the boundary. So it is useful that let us look at this cube, okay? If our body is this cube, the boundary of this body is the union of these faces, this one, the 6 faces of the cube, and this edge and this wedge. Okay, we must distinguish between faces, which are surfaces, and edges, which are curves, and wedges, which are points. Okay, so the boundary of our cube is not a smooth manifold with a continuous varying normal. The boundary in general of a body which we consider in our mathematical modeling are volumes, so subsets of CR3, okay? We have volumes, and the boundary of this volume is the union of faces, edges, and wedges. So what we are considering is a piecewise regular boundary. So in each phase you have a normal which is varying in a regular way, and when you arrive at an edge, the normal is jumping. So on this phase, the normal is EX, and here the outer pointing normal is minus EY. Okay, so here on this edge, you have a jump of the normal. And remark that in this particular regular case we have, but this is not true in every case, here EX is a tangent vector. to the edge. Then you have points where different edges are concurring. Okay, this is standard solid geometry with some concepts of differential geometry. Why? Because we are talking about normal vectors and the variation of normal vectors along one face. In this particular case, the normal is constant, but imagine to have something like that. You have a cylinder, and at the top of the cylinder, you have a spherical, the drawing is horrible, I agree. At the top of the cylinder, you have this spherical surface, okay? Then the normal here is continuous, okay? But you have that on the part of this, so this volume has one face, which is the union of the lateral wall of the cylinder, this one, and the spherical part of the boundary. This is one face, and the other face is the bottom of the cylinder. You have here on this part, you have a jump of the normal, okay? And here you don't have wedges, okay? So you must imagine every body whose boundary is constituted by different faces, edges, and wedges, okay? Now, this face, consider, for instance, a disk. This is an embedded bidimensional manifold surface in R3. This surface has a constant normal, and it has a border, or you can call it boundary, which is the curve ending the surface. You know, you have closed surfaces. A sphere has no border, okay? And you have surfaces with border, like a disk, like that, okay? Okay, and we have on the boundary of our body, we have this kind of integral, and we want to integrate by parts. So the idea is, can we generalize divergence theorem, which we have proven, whose idea of proof we have studied last time can be understood, generalized? Okay. Let us use a standard trick in mathematics. We have a theorem which we have proven, and we want, which regards a formula, and we want to generalize this formula. So what we do, we try to reduce the demonstration of the new formula to the theorem which we have, by using the theorem which we have already proven. So we will prove a formula of integration by parts on a surface by exploiting the divergence theorem which we have proven in the volume. Okay. How we do it? By the way, this is the idea of Paul Germain. So mathematically speaking, this technique is known since probably Riemann. However, it was Paul Germain who applied it to second gradient continua. Okay, so we have one surface this surface has a normal field continuous defined everywhere until this normal is well defined until the border or boundary of this surface. Then you have W parallel, which is a vector field which is tangent to the surface, okay? And then we need some geometrical concepts. We have the border of M, of the surface M. So please don't confuse the border of a volume, which is union of faces. The border of a face is a curve. Okay. Gamma is included in the border of our surface, and this gamma is a curve. And each curve belonging to the border of M is concurring in points, which are the wedges. Okay. Now, what we have a tangent vector T to each curve constituting the border of the surface N, okay? And then you have here, okay, maybe we should make this drawing a little bit clearer. Maybe it is confusing, this W there. So W parallel, we will write here. So everywhere on the face, we have W parallel. Okay, so these are arrows representing W parallel in every point of the surface. And when you arrive here, you have the normal N to the surface, the tangent T to the curve gamma, and nu. What is nu? Nu is orthogonal to gamma, but it is also orthogonal to N. So this is called the normal vector to the curve gamma, which is orthogonal to N. Okay, look, if you have this curve gamma here, in this point here, you have the tangent vector T and the orthogonal plane to T. Okay. In the orthogonal plane to T, you have the normal N to the surface. So you have T and N, two vectors in every point of gamma. And then nu is orthogonal to both N and T, and it is pointing outwards. Okay, so if T is parallel to gamma, nu orthogonal to N, nu orthogonal to gamma, so nu dot T is equal to 0, and this is the orthogonal unit vector to gamma in the tangent plane of M. Okay, and this normal will play an important role in what we will do next. Okay, now what we do? We build a slice. So we are going to build the V epsilon, translating M along the normal. Okay, I'm sorry, here I'm calling capital N, and here I'm calling small n. There is a reason for this, okay? So I'm changing the notation for a while. Okay, so small n is the normal vector to every point of M, our surface. Okay? And we consider a segment along N having thickness epsilon. Actually, we consider for every H belonging to 0 epsilon, we consider the vector H small n. Okay, so for every X in the surface, we add epsilon n, and we have the point X plus epsilon n. So when n runs in M on the surface, you, in this way, are building the surface which we have called M epsilon n, this one. Okay? And for every H, you can build MHN. So MHN is the translation at distance H along N of every point of M. So it is the union of the points obtained with the translation at a distance H along N of every point of M. And our slice V epsilon is the union over H of this MHN. Okay? So you have this slice of volume, which is the union of this. I don't know if you ever, you should, okay. If we had a physical meeting, I could enter the lecture room gifting to each of you an Italian cake, which is called mille foglie, 1,000 sheet, 1,000, okay, 1,000 sheets. This is not the right word. Okay, I will remember it. So if you have eaten this in French, you call it millefeuille. I think that everybody has seen in his life this cake, which is very famous since the French are copying the Italian cake, I think. So you have one layer, one cream, one layer, one cream, one layer, one cream. So you one layer of crunchy pasta, and then one layer of cream, and so on. So you can imagine this slice as the union of these surfaces. Okay, and this is the way in which we are building it. Okay, now you can define W parallel, which is on the surface. You can extend it in the whole volume V epsilon, simply by assuming that it is constant along the thickness. So W parallel in every point in this segment here, and this is the segment X plus epsilon n, along this thickness, this W parallel is constant. So the value which it has at the bottom of our V epsilon, so on the surface M, is always the same along the segment normal to M. Now, clearly, the directional derivative of W parallel along the direction N is 0, because this W parallel is constant along the direction N, which means that gradient of W parallel dot n is equal to 0. By definition, we have defined W parallel in the volume V epsilon in this way. So I hope that you are familiar with the concept of directional derivative of a vector field, which we have discussed in many times. Please, if you have troubles with this, you should ask, we can help, or you can go, if you have healthy readings, you can go to read your book. I mean, the books where you studied this to refresh this idea. So it is clear that by construction, W parallel has normal derivative equal to 0. Okay, so W parallel is prolonged in the whole V epsilon by giving a constant value on the segments x for every x in M, x plus hn, where h belongs to 0 epsilon. So in this way, W parallel was a field on M, now is a field on V epsilon. Okay. So in this way, we are preparing our reasonings. We are preparing the strategy which we have is that we have a field on the surface. Okay. We want to prove something about this field on the surface. We prolong it in a volume so that we will be able to apply the divergence theorem valid for volumes. So this is the trick. Okay, now gradient of W parallel component AB is clearly defined in the same way. So you must be careful. Without the prolongation, this formula were meaningless because XA RA goes from 1 to 3. So these partial derivatives can be done only for fields which are in volumes. Otherwise, these derivatives are meaningless. So the reason for which we have prolonged the surface field in the volume is that we want to talk about these derivatives. Okay. The volume divergence of W parallel is the summation over A of the partial derivatives of the component WA with respect to the variable XA. Okay. So W defined in M has been extended in V epsilon. Therefore, we can apply the three-dimensional divergence theorem for W parallel in V epsilon. How did I wrote V epsilon at the top? How did I write? I wrote this way. Okay. So knowing that this is meaningful, because we have extended W parallel in the thickness V epsilon, we can say that the integral on the volume of W parallel A dxa is equal to the flux on the boundary of V epsilon. Okay, I've placed epsilon down, it is the same, of W A W parallel A and A. Now, the reason for which I wanted to write small n and capital N is now clear. In this formula, capital N is the normal, the field of normals in every point of the boundary of the epsilon. Okay? Now, let us look at this boundary, the boundary of V epsilon. The boundary of V epsilon is made of different parts. We have the top surface of our slice, the bottom surface of our slice, and the lateral walls of this slice. Okay? And this lateral wall can be written like union over X belonging to the boundary of M of these segments. Okay, this is what we have called lateral wall epsilon. Okay, so let us calculate this integral here. So the flux of W parallel through the normal, through the volume boundary of V epsilon. So let us calculate the integral over the boundary V epsilon of WA and A. This integral here. Okay. Now, let us consider the top surface, M epsilon N. The top surface has the normal capital N here, which is exactly the small n of the surface M. Okay? By construction. Similarly, M has this normal. So the capital N field on M epsilon N and on M coincide, the capital N coincides with the small n. Okay? And this means that this addend is 0 and this other addend is 0. So the flux of V parallel on the boundary of V epsilon reduces to the flux on the lateral wall. Why? Because W parallel by construction is tangent to M. So the inner product of a tangent vector with the normal small n is 0. Now, what is capital N A on the lateral wall? It is the outer pointing unit normal to the lateral wall. Okay? And this is N on gamma is equal to nu. This is what we have seen carefully in our geometric discussion. So at the end, we can say that the flux of W parallel through the boundary V epsilon is equal to the flux of W through the lateral wall, and this flux as nu n is equal to nu on this lateral wall, okay, you must calculate the integral of W parallel in this lateral wall. Now, W parallel is constant. along this, and also nu is constant along this. Okay? So with a simple application of mean value theorem, it is clear that when epsilon tends to 0, this flux is epsilon times the surface integral of W parallel A and nu A. So you integrate along this curve here and apply times epsilon for getting the surface integral. Okay. Now we go to this volume integral. Okay. So we have the divergence of W parallel in the volume. Now the trick is the standard one. You introduce the delta, Kroneger's delta. Delta AB is 1 when A is equal to B, and 0 when B is different from A. Okay? So this formula and this formula, these quantities are equal, and so we have this equality. Then we remember that delta AB is equal to QBA plus PBA. If you have a vector, V, and you project this vector in the tangent and along the normal in the tangent plane of a surface and along the normal of the surface, the projection in the tangent plane here plus the projection in the normal direction gives you the vector. So summing the projection of V in the tangent plane plus the projection of V in the normal direction gives you the identity. And this formula represents this geometrical property. Okay. Now you can split delta into the orthogonal and tangent projection. Okay. You remember that this we have proven last time that QBA is equal to NB NA. Okay. So the first addend here becomes this addend. Okay. This is the normal gradient of W parallel, which is 0. So this divergence here, the integral divergence, reduces to this integral in the volume. Okay. So at the end of the story, we have that this volume integral is given by the integral on a surface times the thickness of every segment, which is epsilon, and the flux is given by the integral on a curve times epsilon. So you write this equality here. Okay. You simplify epsilon. This way. And what you get? That the flux through gamma of W parallel this is a line integral, is equal to the integral on M. You remember the idea of divergence theorem of something applied to W parallel, the area. You know, divergence theorem says that when you have a surface, a bidimensional surface, and its boundary is a union of curves, okay? What is here, the operator which we have here, applied to W parallel, which gives you the flux, is what we call the divergence of W parallel. And Gauss has proven the existence of this divergence for volumes having boundary surfaces. Now, what we have proven with our trick, which is not a trick, it is a demonstration idea. We have proven that this operator here, which we call div M, because this is related to the surface M of W parallel, component, I don't know why I wrote A there. Okay, div M W parallel is exactly this operator. So you calculate the partial derivative of WA with respect to XB, and then you saturate with the projection in the tangent plane. So if you like, we define div M W parallel like d W parallel A dXB PBA. This is a definition which is due to Riemann. Okay. Okay. So the divergence theorem for surfaces is given in this way. You take a vector field W, you project it in the parallel plane to M. So this is a parallel vector field, which is here. Either you calculate the flux along the boundary border of M, considering the outer normal tangent vector, or you calculate the integral along on the surface M of the surface divergence. This is a line integral. This is a surface integral. Okay. You get the same result. Okay. So now, before we proceed, we must understand a little bit which is our situation. You have a body B, its boundary B, and then you have that the boundary B is constituted by the faces F1, F2, Fk. You have K faces. Okay. Integrating by part on B, you get some integrals on the faces. So let's go and copy the structure of our integral, this one. Okay, so let me erase some of the okay. We have this integral on the boundary of C star. Okay, I've called it B, so it is better if I keep calling C star. You have C star and the boundary of C star. With our integration by parts, we have got this integral. We'll go back to see how we got this integral. Okay. In this integral, we have exactly this divergence operator. You know, this one. D over dxb, pba, pcb, d over dxc of delta ki. Okay. So our idea is to apply divergence theorem for, as we did before, for moving this divergence operator on the other side of this product in our integrals. This is what we want to do mathematically. Okay? Very well. We have the boundary of C star. The boundary of C star is made of many faces. Look, this horrible drawing. You have the face F1, the face F2, then you have the face F3, and so on. Look, these edges are not straight. In general, they can be curves. Okay, they are concurring in wedges. And you have normals to the face F1, F2, F3, Fk. Okay, these normals are normal fields. Then you have tangent vectors to the curves, so to the edges. And then you have new vectors, normal the edges in the tangent plane. So as I cannot make very well drawings, let us consider a planar section of our situation. So this is the face F1. This line represents the intersection of one plane with the face F1. This is the face F2. So you have the normal N1 and the normal N2. Okay, then you have new one, the outer normal to the curve, which in our section is represented by this point, and the outer normal nu 2 to the same curve regarded as a face, as a border of F2. So this curve here, gamma, can be regarded as a part of the border of F1 and a part of the border F2. So you imagine to have this edge, you have this normal here, this face here, and that face there, okay? And when they glue in a curve, which is drawn I'm trying to draw it there. Okay, on this curve, you have the normal N1, the normal N2, the tangent normal nu1, and the tangent normal nu2. When you integrate by parts, integral over C star of volume divergence of something equal to the flux on the boundary, which is a surface of this something dot n, of course, the curves play no role because the area of these curves is 0. And the integral on something having area 0 is 0. So this integral here can be split. This integral here can be split in the sum of integrals over the faces. So you can write that integral over boundary of C star of S I B P C B d over dx C delta Ki. This can be written like summation over alpha from 1 to k of integral over the face f alpha S I B P C B d over dx C delta Ki. Okay? And this is a trivial decomposition of a surface integral here on the boundary of C star as summation of integrals on each face. Why I'm doing this? Because the divergence theorem, which I've proven here, is valid only on one face, because I need the regularity of the normal of the surface where I am applying this divergence. So this divergence theorem is valid only for regular surfaces. Okay. So I can apply it only for each face. Okay. Now, here we have the really delicate point in our discussion now. So what I will do now, I will consider only one face. So I consider integral over f alpha, sorry, of S I B P C B d over dx C delta Ki. Now I will do a trick, which is not so bad because we all know that P square applied to a vector is equal to P applied to a vector, because if I project the projection, I get the projection. Okay? So I can write that P C D P D B is equal to P C B. How can I calculate the square of a linear map? Multiplying the matrices representing the linear map. So summation over D is the row times column product of the representative matrix of P. And this equality is trivial. I need this equality because I want to replace PCB there. So I will have P D B, and I will have here P D C. So I've simply applied the property of projections. The square of a projection is equal to the projection itself, and I have written it component-wise. Okay? Why I'm doing this? Because this is surely a parallel. So this is S parallel, because I have the projector applied to B. So if SB is not tangent, I don't know what it is. But once I apply PBD, I have reduced it to a tangent vector. Okay? So this is surely S parallel. And this is the divergence. This is the divergence. Surface divergence, which we painfully have proven to appear in the surface divergence theorem. So we will do these reasonings slowly. It is better if we do them very, very slowly. And in case we repeat them several times. Okay. So now I will do a simple, very simple integration by parts. So I write this integral over F alpha of S I B P D B d over dx c delta chi P C D. And I place a bracket in this way. Okay. Now these calculations are very easy. The difficult thing here is not to follow the calculations. The difficult thing is to know which is the right path producing the result, which is not trivial. Okay. Now you can write this d over dx c of S I B B D delta chi minus I have this times that in the previous, so I must write d over dx c of S I B P D B delta chi everything times P C D. So this P is outside, the standard application of Leibniz rule. So you have d over dxc of this quantity. Okay. Now you have this, which is here. Okay. And this, sorry, this, which is here. Yes. So you make d over the first factor, which is here, times delta ki, okay? And d over dxc of the second factor, which is there, okay? So this is the standard integration by parts procedure. Okay. Now you have integral over f alpha of minus d over dxc s I b p b d delta ki p c d. Okay. And you have plus integral over f alpha of d over dx c of s I b p b d delta ki. Okay. Now I can recognize immediately that this first addend produces integral over fa alpha of what? Minus d over dx c s I b p b d p c d. This is a surface divergence of this tangent vector delta ki. So let us start discussing this term. Okay, here, of course, I forgot, and this will be deadly in future. Here I forgot P, C, D. Okay, so the first addend we have there, this first addend is what? This is a work made by a surface force on virtual displacement. Okay. So this quantity is, okay, so maybe it is better if we call in this way. Let's call it 1. And this is 2. So this one is integral on a phase of something, inner product delta k. Remark that this I is the only Eulerian index which we have. Okay. The work is expressed as an inner product in Eulerian coordinates. Everything else is Lagrangian in our reasonings. Okay. So we have a quantity. This quantity is an energy. Okay. This energy is the inner product of a density, surface density of force, inner product, a displacement. Okay, so minus d over dxc s I b p db p c d is a force per unit area. Okay, this force per unit area represents a term in contact forces that did not exist in first gradient continua. And it has a novel structure. Okay, maybe it is now worth to remind you that in first gradient continua, I repeat something which I said to you at least 3 times. You start with integral of p grad delta k, you integrate by parts, and at the end you get integral of div p dot delta k in the volume with minus plus integral on the boundary of C star of Pn delta k. And I'm sure that you have heard about Cauchy so-called postulate. Which tells you that contact normal contact surface depend only on the normal. Okay. I'm sure that you have seen the tetrahedron argument. You have built this tetrahedron. You have applied balance of force at this tetrahedron, and painfully you have proven this dependence on the normal depends linearly. This is the linear dependence is the result of Cauchy tetrahedron argument. Okay. this is a way of considering the integration by parts. When we have applied the integration by parts, we get as a result that contact normal forces depend linearly on the normal of the boundary. Okay? So every first gradient continuum has contact forces depending linearly on the normal of contact surface. Okay? Let us go to the new result. This one. I want to copy it. What happens in gradient continua? You remember what is P? P is the projection in the tangent plane of the contact surface. Okay, on the contact face. This difference is important. So at the end, you have that P plus Q is equal to identity. Okay, so P is the identity minus Q. Okay, so P dB is equal to delta dB minus ND and B. Okay, so let us look at this expression here. I have minus d over dxc of SIB, and here I have delta dB minus ND and B. I close the bracket and I get PCD. Okay, and I'm going to make very interesting, I will make interesting discoveries, because what I have minus d over dxc of SBI delta, okay, delta dB PCD, okay, plus minus minus becomes plus d over dxc. Okay, I'm jumping too many passages. Let us split and then make the subsequent calculations, otherwise it becomes complex. So I have SIB delta BD minus SIB and D and B, which is what we have here, PCD. Okay, and this is correct. Then I have minus d over dx c s I b delta db p c d, and then I have plus d over dx c s I b and d and b p c d. Okay, delta is constant, so it can get out of the integral. So I get minus d over dx c s I b delta, so p c b. So we have another divergence, surface divergence of S, plus now we have this very strange situation. We have d over dx c s bi and d and b p c d. Okay, and this and d p d c gives you 0 because you are projecting the normal in the tangent plane. So this becomes 0. So this disappears. So you are left with S I B d over dx c and d and b p c d. And you will see now a remarkable novelty. You will get d over dx c and d and b plus and d over dx c and b p c d. Okay. Now and d p d c another time is 0. So this term disappears. Okay, but this term survives. Now let us check what is this term. You have that ND is equal to 1. The inner product of the normal with itself is 1 because it is a unit normal vector. Okay, so you can calculate d over dx c of ND and d. What is this? This is d and d over dxc and d 2 times equal 0. If you have a surface and you calculate the derivative, the gradient of the normal to the surface, this gradient is tangent to the surface. Okay. So when you consider d and d dxc p c d, this is equal to the gradient of n. Okay. Do you know how we call the gradient of the normal to a surface? It is the curvature of the surface. When you have a normal which is changing, you have an embedded surface sigma. I'm drawing only a section in a plane. You have an embedded surface, and you have that the normal is changing. It means that the surface is curving. The change of the orientation of the normal tells you the curvature. So this is the curvature of the surface. Okay? What we have proven in second gradient continua, contact surface forces depend on the curvature of the surface. Now, why one should never call Cauchy postulate the assumption made by Cauchy about contact forces. Maybe I cannot invite you to hear a lecture of history and philosophy of science, which I made some days ago, because unfortunately I made them in Italian, but maybe I must do it in English, because I think this is a crucial discussion to be made now, and you deserve to understand these details. Let us think about the word postulate. What is a postulate? Let us give an example of postulate. Okay. An example of postulate from mechanics. Galilean mechanics. I'm sure that you have heard about this postulate, so we can discuss about it, I hope, rather easily. Okay. In mechanics, you usually start with a definition. You call inertial observer or inertial system of reference an observer such that every observed material particle which is free, so it's not interacting with anything else in the universe, okay, moves with a linear, rectilinear, uniform motion. This is a postulate. In mechanics, we can say this is the postulate. The first one which came clear in the mind of mechanicians, okay, or one of the first. Are you talking about a specific? Okay, this is a definition. Sorry, I'm running too much. The postulate is, sorry, the postulate is there exists an inertial observer. So what we say, and this is the postulate. Sorry, I was running and I believed to have already said the postulate, okay? So what we say, we make a definition, this one, and then we accept that such an observer exists. Then I'm sure that you have seen that if I assume that there is one inertial observer, then I'm sure that there exists infinite inertial observer. Why? Because every observer moving with a rectilinear uniform motion with respect to the previous observer is, again, inertial. Okay? So it is enough to postulate the existence of one inertial postulate for one inertial observer for knowing that there are infinite inertial observers. Okay, so a postulate is a statement about every observed material particles. This is it is a statement conjectured to be true for every studied object. Okay? And it is universally valid. It is assumed to be universally valid. of course, in a certain set. Okay. So, in a sense, you must be ready to accept this. Can I prove experimentally the validity of this kind of postulates? Of course, I cannot. Because even if I have observed 1 million observers, so I'm very careful. I organized 1 million of different observers. And these observers observed each another million of free material particles. You can never be sure it's not a material particle which is free and it is not moving with rectilinear uniform motion. So a postulate is an assumption which we hope is true. It is at the basis of our reasonings. And we use this postulate for deducing theorems in our theory, hoping that our theory is predictive. Okay? If our theory gives a prediction which is not valid, then we must change one of the postulates which we have accepted. Okay? I give you an example. Mars is moving in a way in which the postulates of classical mechanics are not are giving us a wrong prediction. In classical mechanics, the motion of Mars is not predictable. So you need to change one of the postulates of mechanics and when you change the right postulate, you invent relativity. So the main idea is that you change your postulate so that it is not true that the change of observers produce the same length. So length and time intervals are not objective when you change observers. Okay, and we said this at the beginning of our lectures, this kind of postulates. So you change the objectivity of time intervals and lengths. Instead, you say that the speed of light is the same for every observer. With this small change of postulates, you manage to describe the motions of every planet in the solar system, including Mars. So you understand that the concept of postulate is much more general than declaring contact forces depend only on the normal of surface, contact surface. Why? Because if you assume that deformation energy depends only on first gradient of placement, then it is true. Contact forces depend only on the normal of contact surfaces. However, if the deformation energy depends also on the second gradient of placement, our simple calculations prove that contact force depend on the curvature of contact surface. So contact forces may depend also on curvature of contact surfaces, simply changing the deformation energy. So this is not a postulate. This is a constitutive assumption. While accepting that contact surface depend only on the normal of contact surface means restricting the possible deformation energies you can use. So this is not a postulate. This is a particular assumption which is valid for some materials, and it is not valid for every material. So it is not a universal statement. It is not a statement which must be valid for every material. It has so-called Cauchy postulate, which one never should, this word should never be associated to Cauchy in this context, is valid only for a specific class of materials. Those materials that can be described by using a particular deformation energy. W E def equal integral over C star of W of F d volume star. So when, for any reason, maybe a complex microstructure E def is equal to integral over C star of W F grad F d V star, then contact surface forces depend also on surface curvature. Okay, it is astonishing that you can read written this more or less clearly in Piola 1848. Okay, but this concept is not very clearly, explicitly written. But then you find in modern literature, Tupin, Midlin, Germain, Sedov. By the way, this man was the head of atomic program in Soviet Union. So it's not a stupid man found in the middle of the street. Paul Germain was the secrétaire perpétuel, the big, the head of the French of Science for Mechanics. Midlin has been a famous mechanician in United States. Tupin became the head of IBM research department. I mean, these are all outstanding persons, and they were totally ignored. And in 95% of books in engineering, you find written that Cauchy postulate is valid for every material. Okay? Okay. Now, these are not the only peculiarities of second gradient materials, because we made some calculations. Let us go back. We made calculations for quantity 1. Okay. We have left also with quantity 2. And this is what we will do slowly. Now. So let me do it in a better way. Okay, let's go down. Okay. In our integral, in our integration by parts, we have also the quantity 2, which is another thing which is very peculiar of second gradient materials. So let us examine this term slowly. So just for having an idea of what we are doing, let us assume to have this simple volume. This is a parallelepiped. Okay. We have done integration by parts. So we have phase F1, phase F2, F1 as normal N1, phase 2 as normal. I should prepare some slides for this. So you have phase, this is N3 and this is phase F3. Then you have N4 and phase F4. Okay. Then you have this phase N5, F5, and you have at the bottom, so let's try to make this, and this is N6, and you have the phase F6. So you have, in this particular case, you have 6 phases, okay? The normals for each phase is constant, so it is continuous. And so you can apply divergence theorem to this integral. So the divergence theorem, which we have proven for surfaces, tells us that, let me copy another time this. So what we have? We have that 2 is equal. So I can replace to d over dxc pc d d on the boundary of the phase. Okay. Now, what is the boundary of the phase 1? If this is the outer normal, the boundary of phase 1 is this curve we run using the right-hand rule. This goes in the direction of the normal, and the hand goes in the direction. So we have this way. Okay. So when you calculate this integral here on the face, you can replace on the boundary of the face the flux of the quantity in the brackets. Okay. Now consider the curve gamma 1 here, this gamma 1. Okay. The integration by parts from the phase n f1 having normal n1 gives you integral over gamma, and this is the direction t, okay, of s I b p b d delta ki nu d. Then you make the integration by parts on the phase f5, and the curve, the cycle you must do is opposite. So you have plus integral over gamma minus t of s I b. So now I must write a symbol. So this is 1. This is nu 1. This is S1, P1, because delta k is the same, because it is a virtual displacement of the edge. But this is for the phase 1. Okay? And then you have the phase 5. So you have S5B, P5DB, delta ki nu 5D. So you have the limit of the quantities. Let me do this drawing. This is the phase 1, and this is the phase 5. Okay? Okay, let me be a little bit more general. I don't want to draw this corner pi over 2. So this is n5. Okay? So nu 5 is this one. Nu 1 is this one. Okay? So you see that this quantity 5, in this quantity 5, you have nu 5. You have the projector in the tangent plane of the phase 5, which is this P. And you have S calculated on the side 5. Okay? Then you have nu 1, P1. So the outer tangent normal to the edge relative to the border of the phase 1, the projection in the plane tangent to the phase 1, and the field S calculated on the phase one. Okay, so get this equal integral over t over gamma. You consider gamma with gamma t. Okay, you must change the sign because this integral is made with respect to one side or another one. Okay, but let us write it in the simplest possible way. You have S1 IB P1 DB nu 1 D plus S5 IB P5 BD nu 5 D integrated over DL. Okay. Sorry, I'm jumping. I wanted to write something. I didn't write it. So I will do it now. Of course, this is delta Ki dl. So what we have? We have a line integral representing an energy obtained with the inner product of a quantity, density per unit line, times a virtual displacement. Okay. What is this quantity? This quantity is a force per unit line. So this means that in second gradient materials, one can observe forces per contact forces per unit line on the edges of the body. This is a totally new. This is totally new. How new is this? Let us go back to Cauchy. The idea of Cauchy was the following. Instead of postulating the principle of virtual work or the principle of minimum energy. Cauchy wanted to postulate the balance of forces, balance of moment of forces. Okay. One will observe that he adds also other postulates. Okay, but they are already two. Okay, so we can observe that we have already two postulates instead of one. And Occam razor is teaching us. Where is Occam razor? Occam razor tells us that when one has two alternative possibilities, either postulating many things or postulating only one thing, it has to be preferred, if the results are the same, that one postulates the minimum possible of postulates. Okay. But remark that Cauchy postulates some necessary conditions for equilibrium, as proven by Piola. Okay, so we know that if we have the balance of force and if we have the principle of virtual work, then balance of force and balance of moment of forces is necessary to equilibrium. So balance of force and balance of moments must be true whenever the principle of virtual work is valid. Okay. It is always true the vice versa. So balance of force and moment of forces is sufficient to the principle of virtual works? The answer is they are sufficient only for first gradient continua. Okay, and now we try to understand why. What is doing Cauchy? He takes a body, then he takes inside of a body a tetrahedron. So this is the point X. Okay, this is EX, EY, E zeta, and then the face to this, the normal to this triangle here is minus EY, okay? The normal to this triangle here is minus EX. The normal to this triangle there is minus E zeta, okay? And then you have, I cannot do very well the drawing, so I repeat it. And then from a different perspective, you have this normal N, which is normal to this face of the tetrahedron. So I'm sure that you have seen the argument which tells that Tn, the vector surface force on the face of the triangle, being the face normal to capital N to the Cauchy tetrahedron, is equal to summation over alpha from 1 to 3 of T E alpha. Okay, alpha is X, Y, zeta. Okay. And how Cauchy is getting this result, which, by the way, is trivial after integration by parts, following Piola's approach. He writes the force, the resultant of the forces on the tetrahedron equal to 0. So he writes that Tn plus T over minus Ex plus T over Ey plus T over minus E zeta is equal to 0. Then he knows the action-reaction principle, making another argument, and he proves this. Okay, but follow now the weak point of Cauchy approach. We have some edges in our tetrahedron. So these are not all the forces. You have some forces eventually applied on the edges of this tetrahedron. So here, this equality is false for second gradient material. For second gradient materials, the tetrahedron argument is not correct as edge contact forces are missing. So even if you may believe that our process of integration by parts, which led us, after many computations, to write, for instance, this expression in the principle of virtual work, which allowed us to discover that you have a dual quantity for delta key I on the edges. You may believe that this is very complicated. Okay, I think that you must do simple standard calculations. So you should not invent one after the other many ad hoc assumptions, and the followers of Cauchy claim that these ad hoc assumptions are driven by experience. They save everything telling that this assumption, whatever it is, is driven by experience. Okay, so absence of edge forces, they say it is experimentally given. Okay, so I can ask them how they can cut out of a body an imaginary tetrahedron and how they can measure the absence of edge forces there. So I think that our process of integration by parts is starting from a very sound basic principle. Minimum of energy in stable equilibrium drives us, gives us a sound, solid, mathematically consistent result. Okay, I think it is moment to stop. This was a very difficult lecture. I will repeat some aspects of this lecture tomorrow. I have left out another important term in the expression of virtual work. The expression of integral on the boundary of C star of sounding dot d over dn delta ki. This is completely new. It is not a standard force. Germain calls it double force. And we will discuss this in detail tomorrow and probably even Thursday. Okay? So I think you must meditate, you must ponder, you must think about what we have said today. Please look at the video recorded lecture. It is very important that you understand all details. Okay, Alessandro, you can stop the recording.